So our topic was a chopper stabilized amplifier. It was called a chopper because the input signal is chopped before going into an AC amplifier. The chopping performs what is known as frequency translation. Frequency translation is necessary because we want the signal to be modulated with the voltages of the AC amplifier. So we're calling it also modulation. And this is a pulse amplitude modulation. And I told you to go and revise your telecoms, revise the sync function, because the sync function, we're able to get the frequency spectrum of rectangular waveforms. And how the amplitude of the spectrum changes as we change the width of the pulse. When the width of the pulse is almost zero, which we call the delta function, then the spectrum is linear from the lowest frequency. The amplitude is the same from the lowest frequency to the highest frequency component. For most of our problems, let us consider the chopping frequency to be maybe a square wave. And if you do the same the square wave, you find that you tend to get the fundamental frequency, third harmonic, fifth harmonic, seventh harmonic, all the odd harmonics, and the change of the amplitudes. So the actual amplitudes can be obtained by convolution theorem. So that's the field of telecoms, which I want to go into here, but you should know it. For us, we perform modulation by chopping, hence the name chopper stabilized amplifier. What chopping does, the information signal is translated to a higher frequency. So if chopping is done at, say, 10 kilohertz, and the information signal with a slowly varying DC signal, then the signal will be translated from a base band of the slow varying DC signal, which we said is less than 1 hertz, to around 10 kilohertz. I hope the student who wrote to me an email that he was not there in the list, I hope he's there in class. I don't know what it's called. Starting with G. I forget his name. Yeah, Calvin. Okay, so let's continue. So the chopping performs modulation. The chopping performs frequency translation. Frequency translation is necessary because we want the information signal to be well above, the information signal frequency to be well above the drift voltage frequencies. The drift voltage frequencies are very low. So that way, When we recover the signal at the end of the chopper stabilizer amplifier, we'll be able to discriminate between the drift voltages and our information signal. But we'll reach there later on. So let's continue. So to perform the chopping, we said we needed some switches. So you have the semiconductor switches, which constitute of BJTs, FETs, and MOSFETs. BJTs, we said, are never used because the offset voltage of the BJT is quite large. So in the last class, I drew a diagram like that, whereby the 50 millivolts is towards the left here, is the signal we want to chop, and its output on this side, and we got, say here, an NPN transistor in between, acting as a switch for chopping. So we know that for a BJT transistor, if it is a silicon transistor, then when the switch is closed, or when the transistor is conducting, there's an offset voltage of about 0.2 volts for small signal silicon transistors. For germanium, it's about 0.1 volts. So since we have 50 millivolts coming inside, there's no way a signal is going to come at the output over here. Okay, because all the voltage drop of 0.2 is necessary across the switch. It's lost across the switch, which is your collector emitter junction of your transistor, of your switching transistor. And then the other disadvantage of the BJT is that for it to chop, if it's an NPN, the collector must be positive with respect to the emitter. And if the signal at the input changes its polarity, so that the collector is negative, then the transistor cannot operate in that region or in that mode, because the collector emitter junction will be reverse bias. So the BJT is never used because of the large voltage drop across the collector and the emitter when it uses a switch. And also, it only chops in one direction. So we never use it. So we read these notes about the BJTs in the last time. Now, the next switch that is commonly used is the FET, or the field effect transistor. Now, the field effect transistor is used because it has got the following advantages. Number one, there is no offset voltage between the drain and the source. If you remember the characteristics of the FET, they pass through the origin. They pass through the origin. So if I were to say, we'll come to it later on. Maybe for some of you have forgotten. If you were to draw the characteristics of an FET, the drain voltage versus drain current, hello, I'm a bit busy. I'm having a meeting. I'll call you later. Sorry for that interruption. I just drawn two characteristics over here, or two characteristics curves. Y-axis is the drain current in milliamps. The drain voltage is in volts. So if you're to magnify around the origin, let's call the origin O. So the currents would pass through the origin. In other words, the drain current can conduct both ways. And therefore, this gives rise to point number one, no offset voltage between the drain and the source. Number two, FETs have a very high switching speed. They can have a very high switching speed. In fact, most of the satellite, we call them LNB, low noise blocks. LNBs is the unit that you put outside, connected to the dish, the satellite dish, to receive the information from the satellite or to receive the electromagnetic waveforms from the satellite. Most of them tend to use FETs, special type of FETs. So FETs can work up to very, very high frequencies. So they have a high switching speed. That's point number two. And then they are bidirectional, i.e. they can chop both positive and negative voltages. This is because if you look at the characteristics between drain and source for various values of VGS, or voltage between gate and source, they pass through the origin. The other thing is that they have a low on resistance. So even though it's not ideal, the on resistance is about 25 ohms for small signal FETs. And actually, there are special FETs with the manufacturer just for choppers. So if you just go to Google and type maybe data for chopper FET, you'll get manufacturers that will manufacture FETs specifically for used in choppers. I think in Google Classroom, I posted some data for this type of FETs. So you have specific FETs which are used for choppers. So the on resistance for this type of FET is about 25 ohms when it's on. So that's what we call RDS on, or resistance between drain and source when it's on. And when it's off, the resistance is about RDS. We call it RDS off. We call it small r, small d, and s to denote its dynamic resistance. And that's typically 10 to the power 10 ohms and 25 degrees centigrade. So even this is not ideal. Remember, for an ideal switch, we want it such that when the switch is closed, the resistance is 0. When the switch is open, the resistance is infinity. But with the practical devices, this is one of the best characteristics that we can get. So I've given some other advantages over there. They're small in size. And also they have very low power requirements, to switch the device on. So we call that control requirement, power control requirements. So this is the driving voltage to the switch. Now the disadvantage of the FET being used as a chopper switch is as follows. They have non-ideal on-off characteristics. They have non-ideal values for on and off characteristics. Why? Because the on resistance of the switch between the terminals is 25 ohms. The off is 10 to the power 10 ohms. Then the other disadvantage is that switching spikes, will come to this in more detail later on, do appear between the output due to, here I've written incomplete isolation between the output terminal and the control voltage. This is due to inter-electrode capacitances. If you are to draw an FET here, for example, this is your drain, source, a practical FET has got a capacitance, CDS, and a capacitance between here, CGD, and a capacitance, CGS. CGS is the one which is normally predominant. So if you're driving this with pulses, rectangular pulses, then depending on the value of the load resistance over here, you're going to get spikes at the output like that. You're going to be getting spikes going at the output of your switch. We shall study this later on in more detail. Okay, so those are referred to as switching spikes. Okay, these switching spikes occur because the driving voltage of the switch is rectangular. And if you have a rectangular driving voltage, if you resolve this rectangular voltage into its spectrum, when the signal rises or the signal falls, this corresponds to the high frequency parts of the signal. And these high frequency parts, well, for high frequency components of the signal, will pass through CGD, or capacitance between the gate and the drain. Let me just check in my notes here if I've got one type of this. Some data for this FET. Where's my FEE501? Let me see here. Oh, it seems I don't have it. We got Google to help us. I used to have them in my notes. Okay, let's go to onsemi. So here's an N channel FET chopper. And there's somebody trying to enter, but I can't admit him because I can't see him. So onsemi is a Japanese company. So this is one of their FETs, which is designed for choppers, small signal choppers. So they'll give you the data, the power, the maximum voltage can, and then some of the characteristics, electrical characteristics of the FET. So for example, the characteristic I told you. So when you just switch it on, this is the static drain to source. When it's on, it's about 30 ohms. It ranges from 30 to 50. And then when it's off, it gives you also data of the intellectual capacitances. So you can see CDG is about 28 picofarads. CDG at 1 megahertz, about 5 picofarads. CSG, when the device is off, is about picofarads. This one doesn't give a lot of information. There's a lot of data about it, but this is not the one I was looking for. This one is very new. I think it's, let me try and help this Google. I think it's a 2N. I know it's a 2N257 something. Let me just try. Okay, let's get out of here. At least I'll download it and give it to you. So these are the disadvantages. Due to the intellectual capacitances, we can either have switching spikes appearing at the output of our switch, which will add to the signal that we are actually chopping and thereby give rise to errors. So that's a small disadvantage, but there's a ways of mitigating it that we shall see later on. Now, the other type of switching device is the MOSFET. The MOSFET is just a modification of the field effect transistor, whereby we use a metal oxide silicon layer between the gate and the channel. So MI stands for metal oxide silicon field effect transistor. So these are nowadays being mass produced. They're nowadays much cheaper than FETs. And they also have some advantages over the FETs. So drain and source is identical to FET, but the connection between the gate and the channel is which is different. There's a metal oxide silicon layer between its input and the channel. And this gives rise to an input impedance typically of about 10 to the power 10 ohms. Sorry, 10 to the power 12. For FET, it was 10 to the power 10. Okay, so because of this insulation layer, for those of you forgotten, maybe it looks something like this. But various ways of drawing it. So this gap is normally shows the metal oxide silicon layer. So the input impedance Ri is approximately 10 to the power 10 ohms. So that means the drive voltage Vc of T that we normally put here, of course it's a rectangular waveform, we'll see a very high impedance. So the power required to drive the MOSFET on or off is almost zero, because the current going into the system, into the gate is almost negligible. So I've said over here that the drain source characteristics is identical to that of the FET, and it requires less power to drive than FETs because the gate is insulated from the channel. And I've summarized by saying of the switching devices, MOSFET implementation of the chopper switch gives rise to the lowest power consumption of the chopper stabilized amplifier. So most of the modern chopper stabilized amplifiers tend to use MOSFETs because nowadays they're being mass produced, and also because of these other benefits. So to put a gap over here to draw electromechanical switches, it's just basically using a relay like the one side drew. So if you can forget about this, I wanted to draw here modulators, chopper modulators, but I drew some in the last class. Maybe I can just, I was supposed to have drawn, for example, you can have a relay over here, the old ones with the electromechanical switch. So this is for a series, the switch is in series. So these are using relays. We don't use them nowadays. Either or you can have even a series and shunt switch. We shall deal with this later on in details. So you have your relay over here. So we call this one S1, maybe this is S2. So this will be called a series, a shunt switch, and these are using electromechanical. So if it's electromechanical, it means it's using relays. We don't use that nowadays. That's so bulky, expensive, consumes too much power. So that's what that gap is there for. So you can forget about it. So we've finished with the first part of our switch, of our chopper stabilized system. So the first part is the modulator, which is the switch, the chopper switch. Now the next part is the AC amplifier. The next part is the AC amplifier. Yes, Odward Davis.
Okay, I wanted to ask, why does the MOSFET choppers actually have a higher impedance?
It's got a high impedance because high impedance between the gate and the channel, because there's a metal oxide silicon layer there. metal oxide is an insulator. That's why we represent it with that gap. The higher impedance is only between the gate and the channel. Is that okay? So the channel is controlled by the electric field around the gate. It doesn't require current to operate like a BJT transistor. Somebody else also raised their hand.
Okay, sir, I think that's well answered. I also wanted to ask, commonly these chopper switches, they actually rapidly switch on and off the circuits, and probably they can be affected by electromagnetic interference. I actually don't get it how exactly the MOSFET comes in to mitigate the effect of electromagnetic interference. How does that come in?
Electromagnetic interference. You see, like now, most of us are using laptops at this present time, right? Some of us are using desktop computers, right? Now, inside the computer, the memories, the processor, some of the combinational logic used, some of the sequential logic used, they all use MOSFETs. Okay? And they all use MOSFETs. I'm sure if you did digital electronics labs in third year, first semester, and you designed maybe some combinational circuit or sequential circuits, there are many logic gates inside one IC. Okay? Of course, most of for the third year experiments, we're normally using TTL, transistor logic. But there are also CMOS experiments. CMOS just means complementary metal oxide silicon. They're just MOSFETs inside, P-type and N-type MOSFETs inside. But let's come back to the computer. Now I'm using a computer here, using a laptop. Inside a laptop, in the processor, there are millions of transistors, which are MOSFETs. In the memory, there are millions of transistors, which are MOSFETs, and very tiny. Yeah? The distances between the two MOSFETs are very, very close. In your mobile phones now, the new generation of mobile phones, if they're 6 nanometers, the transistors themselves are 6 nanometers in size. So they're very close to one another. But there's no interference. There's no interference. Interference will only occur if you have a very large electric field. Okay, maybe caused by maybe lightning or something like that. I don't know if you're together. Okay, so MOSFETs, actually, you people have not done a lot of experiments with MOSFETs, but MOSFETs themselves can very easily be destroyed even when you buy a new one from the shop due to the static charge even of your hands. That's why if you go to a good shop, you find that the MOSFETs, when you buy them, there's normally a conductive paper. It's actually, it looks like transparent, these plastic packages that we put things inside, but it's coated. It looks like it's grayish in color. And then the lids are actually shorted together so that if you touch it with your hand, you don't destroy it, because the clothes you put on, they tend to charge your fingers. And when you're soldering things like MOSFETs into a board, you're supposed to ground the soldering iron. Okay. Otherwise, a normal MOSFET, if you're switching it on and off close to another MOSFET, there's almost very little interference. Very little interference. With the power supplies of computers, if you've seen like the power supplies of things like desktops, they're normally shielded in a metal. They're normally shielded in a metal to prevent radiation from that switch mode power supply. And there are government bodies of each of the country, most of the countries, that regulate how much emission is allowed from power supplies. So you find that they're shielded. If you've broken open one of your laptop power supplies, we call them maybe power bricks or adapters, you'll find that they're shielded. Okay? But if you break open, say something like your mobile phone charger, there's no screening. If you break open your mobile charger, it also uses a switch mode power supply, and it uses MOSFETs inside there. There'll be very little radiation from it. Okay, so there'll be very little interference if the system is designed properly. And if you are scared of radiation, then you can use electromagnetic shielding. You can put your amplifier inside a metal case or a metal foil. Okay, and that's what they do. Like if you've got a high quality laptop, you'll find the power, if you break open the power supplies or the power bricks, as you call them, you'll find that there'll be an aluminum shield inside that prevent electromagnetic radiation due to switching to interfere with things like radios, things like televisions, mainly communication equipment. Digital equipment are not interfered with because for the levels for digital switching, inter-DA, you study TTLs, the levels, logic 1 is maybe from 2.8 volts to maybe 5 volts. Logic 0, maybe from 0 to maybe 2.2 volts. And then there's a noise margin in between. Okay, so to destabilize a logic gate requires quite a large voltage. With CMOS devices, especially those used in processors, which use low voltages like 3.3 volts processors using, say, like Core i5, i7, etc. Still, the noise margin between a logic 0 and logic 1 is almost a volt. So unless the electromagnetic wave induces about a volt in your circuit, in the input of your circuit, that's when it might interfere. So I hope that answers your question. I'm very curious why you're so interested in electromagnetic interference. I hope that answers your question. Otherwise, if you were to put two laptops next to each other, they'll be corrupting themselves. If you were to put your mobile phone against each other, they'll be corrupting your mobile phones, but they don't do so. Okay, so let's continue. So I hope I've answered your question, whoever it was.
Yes.
I hope I've answered your question. You'll find that to drive the MOSFET on, the voltage will be about, later on we're going to come to some practical circuits later on. And I think also in the lab, you're supposed to be doing some experiments on choppers. I don't know if you studied their labs. Okay. The control voltages are typically maybe 5 volts peak to peak, because to switch on a MOSFET, I don't know why I can't get this MOSFET I was looking for, but I'm very sure I have it in my notes somewhere. Okay, since you asked for it, let me go back to my notes again. I see, I'm sure I have it somewhere. Okay, I know what I'll do. NTE 469. It's reason to copy this. So, Mr. Dwar, you can see this data. This is a chopper FET manufactured by NTE. So if you look at these characteristics over here, starting from the left, which is called the gate source cutoff voltage. Can you see this gate source cutoff voltage?
Yes, I can.
Okay. So it's typically when the drain voltage is about 5 volts, it's typically from the minimum is minus 0.5 volts. So you can switch the device off with about 0.5 volts. And the largest is about 3 volts. So the interference voltage, so suppose the device was on and you need to switch it off. So some will come out of the production line such that you need at least minus 0.5 volts. Some will come out from the production line such that to switch the device off, you need at least 3 volts, minus 3 volts. Okay? And this is a large voltage. This is a very, very large voltage. Okay? So that's the noise required. That is the noise required, noise voltage required to be there at the gate, be able to change the state of your switch. That's a large voltage. Okay. For example, where you're located, there's a lot of electromagnetic noise. There's transmissions from the mobile networks, there are transmissions from the police, transmissions from the military. There are all sorts of transmissions going on where you are, okay? But they don't interfere with your laptop, they don't interfere with your mobile phones, etc. Okay? Because the voltages have got to be quite large and must be able to pass into your system before there's interference. Okay, so I'll leave it at that. And let's continue. So the next part of our device, our chopper stabilized amplifier, is the AC amplifier. It's called the AC amplifier because it's only supposed to amplify AC. And this AC amplifier is made by using a capacitor in series with the best low noise instrumentation amplifier that is available, and of course that you can afford, okay? And that amplifier is normally a DC amplifier. So I've written over here that this is usually a DC amplifier, in brackets an op-amp, with low drift characteristics to which a DC capacitor has been added so as not to pass DC drift to the signal. It should also have adequate bandwidth to pass all the sidebands. So if I just to draw here, so we've done the first part, which was your modulator. And there's just a switch. So this was your modulator. This is your input signal. So the next part is your AC amplifier. And there what we have is the best amplifier we can afford with the blocking capacitors. So this is the partner we are talking about. So this amplifier is normally an op-amp. So an instrumentation op-amp. Normally it's an instrumentation. Op-amp. Instrumentation op-amps are very low noise op-amps that are usually quite expensive. Actually quite expensive. It's not like your general 741s. But in the labs, you can just use a 741 op-amp. Okay. So we start with VI, which is a very low frequency signal. We chop it. which results in pulse amplitude modulation, and therefore we've got frequency translation. Frequency translation is necessary because your op-amp and the AC amplifier is going to suffer from drift. Even if you've got the best instrumentation amplifier, it suffers from drift. Okay? So we want the frequency of our information signal be very different from the frequency of the drift voltage of the operational amplifier. And then we don't want the drift voltages of the op-amp also appearing at the output of the op-amp. So the capacitor at the input is to ensure that because the chopping device, your chopping device, have many types of chopping devices, their outputs might also have drift voltages. So for example, if VI is 0, we shall see. If VI is equal to 0, the chopping device that you use might suffer from drift voltages, and those drift voltages might go into our amplifier, our AC amplifier, and we don't want that one. So we block it using the first capacitor, C. Let's call this one C1, and the other one C2. They're normally the same in value for our NE. And similarly, if we were just to consider, let's assume we only to consider a normal AC amplifier. Let's assume this was our AC amplifier. Let's assume we ground the input. And we design maybe a negative feedback amplifier. And we ground the input so that there's no signal. Now, we can get an equivalent circuit of this voltage over here, drift voltage, which you call VAO. And even if you ground this, you get an output voltage over here, which would be that minus RF, RI into VAO. So if you are to put a capacitance at the input over here, and the capacitance at the output over here, then the output at this point over here will have to take into account the reactance of the input circuit. So the reactance of the input circuit will be Ri squared plus Xc squared, all root of that, to get the reactance. So if the reactance of the capacitor is very high, then the output at Y will be very small. Okay, so that should be due to C1 and then also due to C2. But that is I'm going ahead of myself. Let's go step by step. So this is our AC amplifier. So the AC amplifier's function is only to amplify AC signals whose frequencies are well above the drift voltages of both the chopper switch at its input and also that of the amplifier itself. So the capacitors, the input and output, act as high-pass filters. They only allow high frequencies to come from its input and only allow high frequency signals to go to the next stage. Now, in the last class, I gave you a simple diagram of an op-amp. Now today, we are going to see the real op-amp. A long time ago, I used to test students with it, but I found the students, they're not so much interested in design. This year, supposed to be in your fourth year. I don't teach you electronics in fourth year, so I don't know what you people do with op-amps. But a long time I used to set exam questions on this, and the students would perform so poorly. So this is the 741 made by Texas Instruments. So this is a high quality 741. Many companies make 741s. Okay, there used to be big companies like Philips, like Siemens. Those are European ones. In America, those Texas Instruments. There's Advanced Micro Devices and other companies in America. The Japanese also make, people like Onsemi also make their 741s. So they've got slightly different characteristics. So in the last class, I've given you, so that's the pinout. So for example, this packaging of the 741, this has got a metal case. This is the most common packaging, the dual inline packaging that we get in the labs. So pin number 6 is normally the output. Pin number 2 and 3 are your inputs. Pin number 2 is your inverting input. Pin number 3 non-inverting, etc. So here's some of the electrical characteristics of the 741. So look at this, the input, the first characteristics, top left, input offset voltage. So the offset voltage will refer to the input, and these are the test conditions here given. When the source resistance is 10K, temperature is 25 degrees. So it ranges from 1 millivolt to 5 millivolt. So for example, supposing your transducer had a maximum output voltage of say 10 millivolts, then 5 millivolts would present 50% error. Okay, so this is input offset voltage. And then is there IIO? Okay, there's some other important characteristics over here. Input resistance at 25 degrees centigrade, and the supply voltage is plus minus 20. It ranges from 0.3 megohms to about 2 megohms. So this will be useful if you want to transfer as much voltage from your source to the input of your amplifier. Another important characteristic is the slew rate, which is about 0.5 volts per microsecond. This is the maximum rate of change that the output can rise. So you should not put a signal which is faster than this. Otherwise, the output will not be able to follow. So this is the maximum rate of change of the output voltage. So it should not exceed this. I didn't see input offset current over here in this. They didn't include it. Okay, there's some parameters here. Let's see input offset current here. This characteristic number 1 from the top left, 1, 2, 3, 4. Input offset current at 25 degrees centigrade is about, ranges from 3 to 30 nanoamperes, and the maximum is 17 nanoamperes. So it means that if you got a light source resistance, that resistance times 79 amperes will give you the voltage going into your op-amp. And this is the interesting one. The next characteristics is called the average input offset current drift. This height varies with voltage. So this is for this one, 0.5 nanoamperes per degree centigrade. Okay, so if the temperature is, I think, this average drift. So if the temperature changes by 10 degrees, the current will be 5 nanoamperes. It will change from the original. Okay, so those are some of the important characteristics if you're to use it as a chopper stabilized amplifier. Now, as an engineer, you need to design this. So that's the internal circuitry. A long time ago, I used to give students to go and simulate this circuit in Proteus. Go and simulate this circuit in Proteus. And very few students would do it. And you're supposed to be in fifth year. The people are supposed to be designing this these ICs. Okay, so in the last class, I showed you a simplified diagram of an op-amp. In fourth year, you studied op-amps in fourth year? CR, isn't it? CR, you can switch on your mic. Both male and female CR. CR. You mean they're not there?
We did op-amps in fourth year.
Why are you people taking so long to switch on? Well, okay, tell me, what did you study in op-amp? What, ladies here, what did you study? Huh? So you studied the design of the op-amps, right?
Not too much.
But you saw the internal circuitry like
Yes,
this?
we did.
Huh? You did study the internal circuitry of the op-amp, right?
We did. We mean we studied the.
Moses, what's happening to your mic? It's breaking. Ama, you put it next to your mouth? Have you put it next to your mouth?
We didn't do the internal circuitry.
Why? And now when you graduate and you go and work with Texas Instruments America, and they tell you to design an op-amp, then what will you do? Okay, I'll just go through an overview of this. So I'll give you an assignment worth 5 marks of the CAT. It will also help you to learn Proteus. Many of you will be using Proteus for your project simulation software. So if we start from the input of the op-amp, this is the two inputs. So you can see the inputs Q1 and Q2 are just what? It's a common collector circuit, right? Q1 and Q2 is a common collector circuit. So that's used to increase the impedance of the inputs. So there's no voltage gain. Whatever signal comes at the base of any of these transistors is reflected at its emitter. And then Q3 and Q4, we are feeding the signal once again to its emitter, but we are taking the signal out at the collector. So that's a common base circuit. So Q3, Q4 are common base circuits. Common base, current gain is unity. Voltage gain is moderate. Frequency bandwidth is very high. Then the outputs appear at the collector of Q3 and Q4, and one output is taken at the collector of Q4. Now Q5 and Q6 are current mirrors. Q5 and Q6 are current mirrors. So let's give a simple value over here. No, let me leave that for the time being. So Q5 and Q6 are current mirrors. And the output is taken from the collector of Q4, which is the same as collector of Q6. Now the signal now goes to the input of Q15. Now Q15, Q17 is a Darlington. Now the resistance seen looking back into the output of Q4 and Q6 is a very high impedance. Because it's 1 over HOE of Q4 and Q5. So this voltage, to maximize its transfer, we need to load it to the high resistance. So the high resistance is obtained by using Q15, Q17. For a Darlington pair, you know that the current gain is approximately equal to beta 1, beta 2. So beta 1 will be, say, Q17, beta 2 will be Q15. So that you don't swamp the voltage at the output of our differential amplifiers, which is Q4 and Q6. Remember, Q5 and Q6 are the output. These are just current mirrors, or sometimes we call them active loads. So for example, the load seen at the base of Q15, the loads resistance or the input resistance seen at the base of Q15, if the emitter of Q15 is 50 ohms, then 50 times beta of Q17 will be the resistance at the base, the dynamic resistance at the base, Let's give a typical example. So at this point over here, the input resistance Ri will be HFEQ17 let's call it 17 times 50 ohms. And the resistance at the base of here, the input resistance over there, will be, let's call it R1 dash, will be HFE15 into, let's call this one R1, into R1. So R1 dash will be HFE15, HFE17 times 50 ohms. So since the currents will be very small, if you assume that both of them are about a HFE of say approximately 200 or 250, let's use a conservative figure like 200. So Ri dash will be 200 times 200 times 50. How many zeros are this? 1, 2, 3, 4, 5 zeros. So it will be 5 zeros. So it will be 20 times 10 to the power 5 ohms, which is 2 times 10 to the power 6 mega ohms. So the resistance seen over here is actually 2 meg. From third year, when you're studying H parameters, you are able to see the current, the resistance seen looking back at the collector of a transistor when the current is small. And there's an experiment you did, you should have got a HFE for like 1 milliamp, 2 milliamps. Not HFE, HOE. 1 over HOE, which is the resistance, should be about 80K. So it means if this, looking back, Q4, you got about 80K there, and this one 80K. So the next part, the resistance in looking back over here is approximately 40K. So our source resistance, driving source resistance, about 40K. The load it sees is 2 meg. So most of the voltage at the output of our differential stage, most of it will go to the input of Q15. Now R11, which is at the emitter of Q17, is connected to the base of Q22. Now this one is just for protection. It's for protection. That's to limit the maximum voltage that goes into Q15, Q17 Darlington. So when the base voltage of Q17 is about, the cut-in voltage will be about 0.5 volts. So when this voltage over here is 0.5 volts, that's when Q22 will start to conduct. So when it starts conducting, it will short circuit any signal coming over here, any signal coming to the base of Q15. So that will protect the op-amp to some extent. So that tells me the maximum current that passes through the 50 ohms. So 50 ohms is the limit of Q17. So 50 times I of 17 should equal to 0.5 volts. So we can get I, the emitter current, to be equal to, let me write it here. It will be equal to 0.5 volts divided by 50. Let's put it into milliamps times 1,000. So it's equal to 10 milliamps. 10 milliamps. So the maximum current allowed inside this circuit over here is 10 milliamps. So that will perform some protection. Hope that is understood. Now let me rub all this so that our diagram becomes clearer. And I used to test these questions in a long time ago, but the students, they never do it. They get 0. Then Senate says, I'm not teaching. I'll ask it as part of the assignment. It will also give you practice. Also, you used to do this in 4th term, the design, but not this. You design a good class B amplifier for the project, what is called a mini project in 3rd year. Not those class Bs you people do in the labs. Those are for baby class. Those things you do in the labs. Okay, so Q5, Q17, this is actually our voltage stage. This is actually our voltage amplifier stage. Most of the amplification is done by Q5, sorry, Q15, Q16. Now, this transistor, which is not at the collector of Q15 and Q17, they didn't give it a number. Maybe it's Q14, Q12. I can't see Q14. It's Q13. It's Q15. Oh, Q14 is there. They didn't give it a number. Anyway, the largest number here was what? Q20. Okay, let's call it Q21. This transistor here. Let's call it Q21. So that is what is known as the VBE multiplier. Remember, in the last class, I said you could just do the same thing using diodes, 2 diodes. So if you use 2 diodes, the voltage drop across the 2 diodes is approximately 1.2 when they're conducting. Cut-in voltage is 0.5, 0.51. So this can be used to bias Q14 and also bias Q20. Look at this output stage. This output stage is a class B output stage, which you've studied, okay? So the function of Q21 over there is to put a voltage approximately ranging between 1 and 1.2 volts across the base, at the base of Q14 and Q20. For example, let's start with the top transistor, which is Q14. For this transistor, just to conduct, the voltage between here and here, because this is a low resistance, the voltage between here and here should be approximately the cut-in voltage when you're just starting to have crossover distortion. Should be 0.5 volts with this side positive, this side negative. The voltage between here and here should also be approximately 0.5 volts when the transistor is just going to conduct 0.5 volts. So it means the voltage between, if I call this point A and this point B, so the voltage from here all the way to here, when you're just eliminating crossover distortion, is 0.5 plus 0.5, which is 1 volt. If you want to eliminate crossover distortion completely, you make it 0.6, 0.6, so it's 1.2 volts. And how you make it 0.6 is using Q21 VB multiplier. I hope you people are with me. Moses, are you with me?
Yes.
So this output stage is what you did in third year, but there's some extra things they put over there for protection. But we're just considering the biasing at present. Okay, so to bias Q14 and Q20, which is our output stage, which is in class B, to eliminate crossover distortion, you need at least 1.2 volts. And that 1.2 volts is provided by Q21. And this network formed by Q21, R7, and R8 is called VB multiplier. It multiplies the VBE of Q21. Now let's see how it functions. Oh, my pen is not working. My pen has gotten discharged, so I'll give it a few seconds to charge. Okay, but then maybe we can do it mentally. You people can do it mentally. They want to find out the potential between point A and point B as produced by the VBE multiplier. Why it's called a VBE multiplier. Actually, it has got two functions. One of them is to ensure that there's no crossover distortion. And the other is to compensate the biasing of Q14 and Q20 so that when the temperature increases, the voltage between point A and point B decreases so that transistor Q14 and Q20 do not go into thermal runaway. They do not go into thermal runaway. And it does so because this is a chip. So everything is integrated into the chip. And the hottest part of the circuit, or the part of the circuit that dissipates the most heat, is the output devices, which is Q14 and Q20. Now, most of these op-amps are normally rated at about the power dissipation maximum is 300 milliwatts. It's rated at 300 milliwatts. Let me just see, we can just go back when my pen is still charging. Power dissipation. So the power consumption is given over here. At this point over here is the power consumption. So at maximum temperature is about 135. At 25 degrees centigrade is about 150 milliwatts. Okay, let's do it mentally when my pen is still charging. So if we start at point B, we move up the VB of the transistor. Then we move up through R7, we reach the potential at A. So let's see how this VB multiplier works. I think my pen is charged. Let's try. Okay, so let's start at point B. Point B and move towards the emitter of Q21. So the voltage drop across R8, which is 7.5, is VBE of Q21. So we can talk of the current through 7.5, the 7.5K. So the current passing this way, let's call it I. So I will be equal to VBE, or 21, over 7.5K. Okay, and therefore the voltage, across the transistor 21 from emitter to its collector will be the voltage drop across the 7.5K plus the voltage drop across R7. And the voltage drop across, so we can, let me just write it at the bottom over here. So we can say, therefore, VCE or transistor 21 will be equal to the current I into R8 plus R7. And this will be equal to VBE, equal to VBE 21, because we got an I from here, VB 21 over 7.5, or over, let me just use those values. Let me just use it as R8 over R8. R8 is the 7.5 into R8 plus R7. So the voltage will be VBE (21) into 1 plus R7 over R8. Wow, that is not very tidy. And write it on top here, it might look a bit neater. So VBE, sorry, not VBE, VCE 21 will be equal to VBE of 21 into 1 plus R7 over R8. I know I'm doing this. Okay. And in this case, remember our R7 is 4.5K. And our R8 is 7.5. It is 7.5. So I've got my calculator today. Let me calculate it. 4.5 divided by 7.5, 0.6. So I'll just write it over here. VCE 21 the VBE, which is typically 0.6 volts into 1 plus 0.6, 1.6. So the bracket becomes 1.6 times 0.6. So 1.6 times 0.6 is 0.9. 0.96 volts. Okay, so with those values, the voltage between points A and B is 0.96 volts. Okay, which is very close to the original design over here, which was 1 volt. If the cut-in voltage, remember the cut-in voltage for the transistor, if I was to draw the left over here, the diagram, the cut-in voltage for most silicon is typically like 0.4 volts. And this knee point over here is actually 0.5. Okay. Now, the interesting thing of this circuit is that, remember this VBE, this outside is 0.6 volts over here. When the temperature increases, it decreases. When the temperature decreases, it increases. The various curves, let me draw on the left over here again. So if this is a temperature, say T1, this is a temperature, say T2, and in this case, T1 greater than T2. So the VB multiplier circuit will automatically compensate for temperature changes so that Q14 and Q15 are always biased at the correct voltage so that there's no thermal runaway. So that is the function of the VBE multiplier. It's called a multiplier because you can see the output is VCE, 21 is VBE into bracket 1 plus R7 over R8. So VB is multiplied by the factor 1 plus R7 over R8. That's why it's called a VB multiplier. Now, finally, there's this Q15, whose base is connected to R9, which is 25 ohms. So that circuit over there performs short circuit protection for Q14. It's only for Q14. I don't know why they don't put 2. for the top transistor Q14 and for bottom transistor Q15. In things like high-powered audio amplifiers, we normally have 2 of them. So this will just give you a bit of protection. So when the voltage across, remember the load current. Let me just rub everything. I hope everybody has taken. But this is supposed to be in 4th year. The design of the op-amp is supposed to be in 4th year. You don't just draw a triangle and say that it's an op-amp and you call yourself an engineer. So for short circuit protection, performed by Q15 and R9. So when the voltage across the base of Q15 is 0.5 volts, Q15 will start to conduct and start decreasing current going to the output. This will be short circuiting current used to drive Q14. So the short circuit protection, so you can say I short circuit for protection of only Q14 times 25 ohms should equal to 0.5 volts. That's the cut-in voltage of Q15. So I short circuit will be 0.5 over 25 ohms, or in milliamps, you can say that I short circuit will be equal to 0.5 volts times 1,000 over 25. 25 into 1,000 is 40. So I short circuit with 0.5 times 40. So this is in milliamps. So this is 20 milliamps. So that's the maximum current you're allowed to drive towards a load. Let's see what the data sheet says. Can you hear? Can you see over here? Output short circuit current over here by 25 degrees is 25 milliamps. So we got 20, maybe they're using 0.6. They're using 0.6 volts. Let's try to 0.6 volts. So if you had to use, instead of 0.5, use 0.6 volts as our cut-in voltage, then I short circuit in milliamps would be 0.6 times 40, which is 24. So they're using 24. They're using 0.6 volts to get the short circuit current. Okay, so the output stage is just a class B. So Q13 is an active load for this Darlington Q15 and Q16. This is just an active load. And the current is controlled by this network over here. The current that passes through Q 13 is controlled by this current mirror over here. And this one, when I used to ask the students, they will not have any idea. I thought you people study current mirrors in your third year or fourth year. I don't know. I used to teach electronics lower classes thousands of years ago, many, many years ago, not now. Okay. So let's get the current through Q13. Let's get the current through Q13. The biasing current through Q13. All class B amplifiers, all these high-powered class B amplifiers, they use a similar topology. It's only the input is slightly different because you don't need a very high impedance. And op-amps, the voltage swing is very little, maximum, approximately the supply voltage. So if you're using plus minus 15 volts, that's the maximum voltage swing. But for power amplifiers, the supply voltage is 100 volts, plus minus 100 volts. Okay, so let's check the biasing of Q15. And last year, I set a similar question to this, but in fact, the last 2 years, but for the multiplier, analog multiplier, and the students never even attempted. They won't even attempt it. Once they see a circuit like this, they say it's complicated, but it's not complicated if you break it down. Now, let's look at this circuit over here. So for this op-amp, the manufacturer tells you the maximum voltage you're supposed to apply is 15 volts. Let's confirm it here. This is the maximum voltage swing. It's plus 14, maximum plus 13. So that's VCC. Supply voltage, how come you're not given here? It's given here. Supply voltage, recommended operating conditions. So the LM741, supply voltage, VDD to ground minimum, plus minus 10. Normal is plus minus 15. Maximum plus 22. Okay, so we use the normal voltage. Normal voltage, let's use the normal voltage. Plus minus 15. So we put plus 15 volts here, minus 15 volts here. So let's check the biasing of the circuit to find the currents passing through our system. So if you short circuit, look at Q12 over here. If you look at Q12 over here, if you short circuit the base of a transistor to its collector, it just behaves as a diode. So this circuit over here is just like a diode. So for Q12, if you have to look at it, it just looks like a diode. So you're going to get this diode junction over here being used. And it's going to drop at least 0.6 volts. So your diode will drop at least 0.6 volts. Between the two ends of the diode. So the current will pass through here. And there's another diode over here, Q11. all the way to the ground. So this will also just behave like a diode. So we got two diodes, and then you got your 39K. So you got 39K, and you got your bottom diode, 2 minus 15 volts. So this bottom diode is Q11. This is your Q11. This is your Q12. Sierra, do you have class after this?
Yes, we do.
Okay. Okay, so let's finish this one. So we can get the current through the 39K. So the current, if we call it I, so I will be the total voltage drop from plus 15 to minus 15 is 30 volts. Minus the voltage drop across the two diodes, 0.6, 0.6. So I'll just write 1.2 all over 39K. Will give you the current passing through. So 30 minus 1.2, 28.8. Divide by 39, with current in milliamps. So you're going to get this will be equal to 0.74 milliamps. So the current passing through this circuit over here is 0.74. 0.74 milliamps. All right. So if 0.74 milliamps is passing through Q, this Q over here, Q11, it must mean that also this one, 0.74. This is also 0.74. Because Q11, Q10, and Q11 are current mirrors. And also Q12 and Q13 are current mirrors. So the current passing through Q13 is also 0.74 milliamps. And this current will pass through here. So the system is working. Also here, this current over here is 0.74 milliamps. Okay, so I'll leave you over there to calculate the various currents. I want us to calculate the various current. Because I want us to calculate this current and also this current over here. Now this Q9 and Q8 here, remember this transistor fabricated in the same chip, so Q9 and Q8 also form a same current mirror. So you got 0.74 passing here. And also in this circuit over here, the collector, I'll just draw it here. Here also you get 0.74 milliamps without any signal. And then this current will be divided equally between these two transistors when the two inputs are grounded. So 0.74 divided by 2. That is 3.7. So here you get a current which is 0.37. And here a current 0.37 milliamps. And this current we must pass over here. This current must pass over here. This current also must pass over here. This current must pass over here. When the two inputs are grounded, when there's no signal, and you bias your circuit correctly. Okay, that's the quiescent current. And then finally, there's this capacitor C1, which is very important, which is connected between the base of Q15 and the collector of Q13, capacitance C1, which is 30 picofarads. I'll talk about it in the next class. But that capacitor is what is responsible for the slew rate. The slew rate of your operation. The slew rate, as I said, is the maximum rate of change of the output voltage. The maximum rate at which the output voltage must change. For the 741, this one, we said it was 0.5 volts per microsecond. Now, what is responsible for that is C1. C1 is responsible for that. So I'm sure in your fourth year, when you studied op-amps, specifications like slew rate was given, but now you see what is responsible for the slew rate. In short form, because time is up, when the current passing through C1 is equal to the current, the signal current rather, when the signal current passing through C1 is equal to the signal current driving C5, and we say that the op-amp has reached its slew rate limit. It has reached its slew rate limit. I'll stop over there.